We propose RAPID, which stands for Robust and Agile Planner, using inverse reinforcement learning for vision-based drone navigation. Our method was trained in simulation, but successfully validated in the real world without additional training. This experiment video shows that the proposed model flies at an average speed of 6.7 meters per second in a forest environment without collision. Previous approaches often used reinforcement learning for visual navigation. However, applying RL methods to high-speed drones increases complexity, requiring complex reward functions and more training samples. In contrast, inverse reinforcement learning infers the reward function from expert demonstrations, eliminating the need for explicit reward design, and is more sample efficient while retaining strong generalization. RAPID takes depth images, velocity, attitude, and a relative goal vector as inputs, generating collision-free waypoints. We use a deeper, dense RL network with skipping connections to produce high-dimensional actions. RAPID has 4 stages. First, it uses an SE3 planner to generate a global trajectory. Second, it collects state action pairs by following waypoints in simulation. Third, it infers the reward function and updates the actor-critic model through simulation interaction. And finally, it converts the inferred waypoints into a trajectory, which is then followed by a controller. We trained the RAPID network in a virtual forest. After that, the trained policy was validated in a randomly spawned tree environment to check generalization performance. Despite its high tree density, the drone successfully reached its goal. Although the RAPID model is trained in tree environments, it shows reasonable obstacle avoidance performance in environments with different types of obstacles. We compared RAPID against existing methods with varying tree density. Simulation results show the proposed RAPID model significantly outperforms other learning-based methods. We conducted experiments in real-world environments. In real-world tests under natural environments, the drone navigated densely wooded areas at an average speed of 7 meters per second, reaching the goal successfully. In urban environments, it avoided a large block by making evasive motions at an early stage of flight. We also tested the model in column environments. In this environment, the drone safely reached the destination by accelerating and decelerating its speed.